Hello, my name is Mina Kemp and I am a student at Tennessee Technological University. I will be talking about my work developing a graphical user interface-based framework for Monte Carlo simulations of ultracold neutrons, or UCNs. The goal of my project was to provide a visualization framework for the UCN Monte Carlo code UCN transport, which simulates the UCN tau experiment. The UCN tau experiment itself seeks to measure the mean lifetime of a free neutron through the use of a magneto-gravitational trap in which UCNs are confined. Simulations of physical experiments such as these require a high fidelity, as these simulations are often used to assess subtle systematic effects in the experiments that they model. Being able to visualize the geometry and results of the simulation itself aids in achieving a high fidelity, as errors can be caught and corrected much more efficiently. One of the things I worked on was improving the file format used to define the experiment's geometry, or its physical shape. The previous format required regions to be referred to by an index, only included box and cylinder shapes, and was split between two files. The new format consolidates these two files into one and refers to regions by a given name, which makes it easier to insert and remove regions, as you no longer have to deal with the resulting cascading shift of indices that you would have to account for otherwise. The new format also allows for the definition of custom region shapes defined mathematically, as well as region states, which allow for regions to move at certain times, useful for things like sliding doors. As for the framework itself, the main feature is, of course, being able to not only view the geometry, but to be able to modify it and see your changes take effect immediately. This makes the process of modifying the geometry both faster and less error-prone. Simulation data can also be superimposed onto the geometry to provide a visualization of the simulation being run. This feature actually required a bit of engineering to accomplish. The initial approach was dubbed the load everything into RAM approach, with RAM standing for random access memory. This approach at first seems perfectly acceptable. Accessing data from RAM is very fast for your computer to do, as opposed to accessing it from a hard drive, which is relatively slow. The issue with this method is that these simulations can output a lot of data, thousands of neutrons worth for thousands of seconds. So the average computer's RAM capacity can actually be less than what is required to store all of the simulation data. Thus, a new approach had to be developed, dubbed the sliding window approach. This approach only loads a portion of the simulation data into RAM at any given time. As you watch the simulation happen, data from the past is unloaded and data to play the future is loaded, such that there is this fixed window of data that slides along the time axis. This is also efficient when navigating backwards through the simulation, as the window tries to center itself around the current time. In order for this method to allow for painless navigation about such a large data set in real time, a custom file format had to be developed that arranged the data for each neutron in a very particular way, organizing them by time in discrete chunks so that they may be loaded into RAM as quickly as possible to maintain smoothness of the animation. In the end, we now have a nice visualization framework for use with our simulation, which will help researchers, especially new ones like undergraduates, do their research in a much more efficient and straightforward way. Thank you.